Our session today. This is the 10th Mount Sinai Winter Symposium in Children's Environmental Health. I'm Dr. Robert Wright. I'm the Department Chair of Environmental Medicine and Public Health. We're really happy that you came here today on this kind of gloomy February day. Unlike yesterday, which was, I think, 78 degrees at one point in Central Park. On that note, one of our talks will actually go into climate change. So I'm going to start with the overall theme of today's talk, which is the future and where do we go from here in children's environmental health. So we're going to talk to you about a relatively new concept called the exposome. It's been around probably in one form or another for about 13 years, but it was first defined, for about 20 years, but it was first defined about 13 years ago. And this is how we're conceiving of the exposome and what our new Institute for Exposomics is going to do. So it's the final piece of the puzzle, and as you can see at the top, there are the measures, whether it's nutrition, we define the exposome very broadly, or social environment, or chemicals, or physical environment, such as the built environment or air pollution. And then there are the resources that we bring, the new Institute for Exposomics, as well as the PACER lab for phenotyping and stress measurement, which Dr. Roswright runs, and she'll talk to you about, and the Lautenberg Laboratory for exposure biomarkers. And then the return on investment. So where do we think, why is it important to study the exposome? Well, it's going to lead to better ideas about prevention of diseases. It's going to lead to diagnostic tests. We think it should be incorporated into the new field of precision medicine, and it's an important part of life course research. So, as I said, we're a relatively new institute. We first established the Frank Lautenberg Laboratory in 2014. As well as the phenotyping laboratory called the PACER lab, which measures phenomics and stress, also in 2014. Since then, we've actually gotten several large grants. We have a NIH CHEER grant, both the lab hub and a data center. So this is actually a grant that actually measures environmental exposures in children broadly, so it's an exposomics program. We also have an ECHO grant. ECHO stands for Environment and Child Health Outcomes. We actually have two of those based here at Mount Sinai. We have a transdisciplinary P30 center, which is a core center which helps to fund some of our research. In total, we've actually brought in over $100 million of NIH funding in less than 5 years. So this is clearly a field that NIH is very interested in. And in fact, it's so much funding that we were recently able to hire Jessica Elba as a laboratory technician. This is her first day in work, actually. So why focus on the environment? Well, there are a number of trends that are happening in our world. There's a growing prevalence of learning disabilities, there's a growing prevalence of obesity, eczema and skin allergies, and even some of the pediatric cancers are increasing. If something's increasing in prevalence over 20 to 30 years, it's not due to genetics. Genetics cannot operate on that sort of time scale. It's actually impossible. And it's not just pediatric diseases. Obviously, adult diseases may increase if they tend to be more prevalent when you're older and our population is aging, but Alzheimer's disease is increasing. There's increasing evidence that Alzheimer's disease has its causes in factors, environmental factors that occur very early in life. In fact, when I was in public health school, I once wrote a paper for a class that actually hypothesized that childhood lead poisoning was a risk factor for later life Alzheimer's disease. And if that's true, we're going to have an epidemic of Alzheimer's disease coming forward. There's also evidence that Parkinson's disease is increasing in prevalence. So all of these diseases clearly have a major environmental component because they can't increase in prevalence purely from genetics. Well, what are we doing to try to understand the origins of these diseases? If you do use PubMed, which is a publicly available web-based search engine to look at research studies, and you cross-reference obesity with genetics, or you cross-reference obesity with environment, you'll find 37,000 studies on genetics and 12,000 studies on environment. For autism, ADHD, the ratio between genetic research and environmental research is still about 3 to 4 to 1. For Parkinson's disease, if you look at adult diseases, the ratio gets even worse. Interestingly, Parkinson's disease is one of the only examples in which a twin study showed that there's virtually no genetic component. There have been a number of twin studies, and in fact, this is a quote from an actual sort of meta-analysis of all the twin studies, and the conclusion was that the results suggested environmental factors are the most important in the etiology of Parkinson's disease, and genetics plays a very minor role. If you do a PubMed search on Parkinson's disease and genetics and Parkinson's disease and environment, the ratio is actually 8-to-1 in terms of the number of studies that look at genetic components or genetic risk factors for Parkinson's disease versus environmental. This is even when twin studies suggest that the genetic component is very minor. So we're not looking at research into etiologies of diseases the way we should be, because environment plays a major role and we're largely ignoring it. And this is because I believe technology drives science. After the Human Genome Project was finished in 2003, the technology around genomics improved dramatically. So in this slide, you can see our ability to measure the genome all the way up to sequencing got much, much better over the last 20 years, and the cost plummeted. That's why there's so much genetic research, because we're really good at measuring the genome. There's absolutely no dispute about that. Whether or not measuring the genome by itself actually tells us anything about why people get sick is a very different question, and I would argue that it doesn't. That genetics itself needs environmental measures if we want to understand it, because almost all genetic diseases, even like cystic fibrosis or hemochromatosis or phenylketonuria, have an environmental component. It's just better understood for those sort of Mendelian genetic diseases. All diseases may have a genetic component, but all diseases have an environmental component and they interact. I would also argue that the technology in environmental health is changing dramatically, particularly in the last 10 years. And environmental health is roughly where genomics was in 2000. So I believe we're at this inflection point where our ability to measure the exposome is going to grow dramatically. And we're talking about some of those changes that are coming. So there's a number of challenges in measuring the exposome that don't actually exist in genomics. The exposome really has no endpoint with respect to chemicals, nutrition, metabolism, physical factors, and social stressors and emotional stimuli. Not everything can be measured in blood either. So you can't measure noise, you can't measure the built environment, you can't measure air pollution in blood. So some of the measurements that we do actually are not blood-based assays, unlike genomics. And then time is the critical fourth dimension. Your DNA sequence never changes. I can measure it at any life stage, and it should be roughly the same. It should be exactly the same without somatic mutations. But it doesn't matter when you measure genetics. It matters when you measure the environment. And there's another issue called critical developmental window. So when you are exposed matters just as much as what you're exposed to. So the example I like to give in my classes is if I'm exposed to a chemical that stunts my growth, and I'm 30 years old, nothing's going to happen because I stopped growing. If I'm exposed when I'm 2 years old, it may stunt my growth. So that's sort of a gross definition of what critical developmental windows are. But for every health component of our lives, whether it's the brain, every organ, whether it's the pancreas, whether it's the digestive system, there are times when it's developing and times when it's not. If you're exposed to something positive or negative at times when it's developing, you're going to see a much greater effect than times when it's not developing. And that's really what critical developmental windows is about. So we have to know not just what you're exposed to, but when you were exposed. So the exposome encompasses all environment. It's not just chemicals. It's nutrition, it's the social environment, it's the physical environment. And this is what we're going to measure in our new institute. So what's the big picture in exposomics? So what are the important research questions in environmental health? And how do we drive the technological changes that are coming to fill the needs that we have? We know that there's roughly 100,000 chemicals registered with the EPA for industrial use. We know that there's thousands, tens of thousands really, of other chemicals, some of them natural, that are found in our food and water and air. Even in the field of environmental health, we've had some problems. We tend to study roughly 50 chemicals over and over and over again. BPA, mercury, DDT, PCBs, phthalates, even lead gets studied repeatedly. No one disputes that lead's not toxic Everyone believes that, yet we keep doing research in lead. Most of these chemicals have actually decreased in prevalence in the United States because of this research. But autism and learning disabilities and obesity keep increasing. So we're also guilty of not studying the right things, because if those diseases are increasing and these chemicals are less prevalent, they're not the major driver of that increase. It has to be something else. It's the environment that we're not measuring. So genetics can't explain those changes, and the way we're doing our environmental health research can't explain those changes either. So how do we increase the pace of environmental research discovery? So that's what we have to shift from. We have to shift from hypothesis testing to discovery. We have to start to figure out what it is in our environment that's causing these changes. And the exposome is actually designed to do just that. So the term the exposome was actually coined in 2005 by Christopher Wild, who's now the director of IARC, the International Agency for Research in Cancer. It's meant to be analogous to the genome. And the idea is we're going to measure the environment broadly. Just like we measure all the genetic variants in our genome, we're going to measure all the variation in our environment. It requires us to shift the paradigm in environmental health research. So we have to emphasize being able to discover what it is that's causing these changes. We need to measure and study the environment more than genetics, or at least as much as genetics, if we're ever going to understand gene-environment interactions. We have to stop looking at one chemical at a time. We have to start with mixtures and then move from mixtures to exposomics, where we're measuring thousands and thousands of chemicals in an agnostic fashion, the way that we measure genomic variants in an agnostic fashion. That way we can discover which are the environmental factors that are most important, and then we can test those in hypotheses. And we have to measure it across the lifespan. And it absolutely can be done. It sounds daunting, it sounds impossible. In 2005, it probably was impossible, but there have been a lot of advances in the field. We can now measure thousands of chemicals in a single assay. That wasn't possible in 2005. There are satellites that circumnavigate the globe, and you're going to hear about some of that work, that predict weather, that predict air pollution, that predict all sorts of different environmental factors that we can now measure. And the world is changing. It's a much different world than when Christopher Wild described the exposome in 2005. How many people have a Fitbit or an Apple Watch in the room? Yeah, I have one too. So Apple knows exactly where I am right now. They know exactly where you are right now. So it's a GPS device. Plus it's giving them all kinds of information about how active we are. So we can actually tie that information to environmental factors like air pollution and climate, and also activity. Our cell phones are GPS devices. I'm sure everybody has a cell phone, and like me, you probably panic if you forget your cell phone and actually will go back home to pick it up no matter where you are in your commute. If you go to the grocery store and you give them that little coupon card, Stop and Shop knows everything that you buy. They have a better sense of your diet than you do, probably, because they keep those records, and they're advertising to you in a certain way, and they're stocking the shelves in a certain way based on that data. That sort of information exists. We have to start to be able to mine that kind of data. Amazon knows what you buy too. It's a similar sort of dynamic. Facebook, Twitter, Instagram, we actually give a lot of social information about ourselves that we post on the web. All of that information is starting to get collated. Businesses are doing it. Researchers are now starting to do it. So the ability to measure the exposome exists. It just requires the will to organize all this information. So some of what you're going to hear about today from Dr. Rohrer is about ways to measure the past. So one of the things that distinguishes our institute and our program is we're trying to go back in time, because we're trying to understand the environmental factors that led to your health today. It's probably not something that happened this morning or yesterday. It's probably something that happened years in the past. So it's very, very important to go back in time. And he's going to tell you about how he uses teeth to go back in time to measure environmental chemicals at specific life stages. Dr. Niedzwiecki is going to tell you about exposomic assays, our ability to measure thousands of chemicals in a single assay and how that's done. These are relatively new technologies, sometimes called untargeted assays. And she's also going to talk a little bit about wearable devices, which are becoming more and more common, that can actually be used in combination with this technology. Alan Just is going to tell you about how satellite remote sensing can measure multiple environmental factors, not just air pollution, but green space, parks, light at night, the built environment, pollen, all kinds of things that actually can affect your health. And then Roz Wright is going to talk to you about the social environment, how social factors get into your body. Many of them actually affect the brain, and the mind-body dynamic actually causes changes in different organs. It can cause changes in the lungs, it can cause changes in the cardiovascular system, but it can actually get into your body and sometimes even interact with the chemical exposures to cause health effects. And then there's the precision medicine initiative that NIH and Mount Sinai is a part of. Precision medicine has largely been genomics, but we know that everything at its heart is a gene-environment interaction. And if we're only measuring genomics, we're only getting at most half the picture. So if we can link genomic programs to exposomic programs, we can measure gene-environment interactions across the lifespan, because they have to factor in those critical developmental windows that I talked to you about. If there's a genetic impact, or excuse me, a genetic susceptibility to a chemical that stunts your growth, you're only going to see it if you measure exposure at the time of childhood when you're growing. And then you can link it to genomics more effectively. So, summary of our exposome research efforts: we're measuring the external exposome, we're looking at wearable devices, we're looking at air pollution, we're doing computer database mining, looking at things like built environment, access to food, remote sensing using NASA satellites. We're looking at the internal exposome. Some of this is wet lab-based mass spec assays, but we're also looking at novel matrices such as teeth, and our program actually specializes in reconstructing the past. So in summary, we've had a lot of success in the last 5 years, and we're hoping in the next 5 years to have even more success. We've already brought in over $100 million of NIH funding. We've established a new institute. That institute is going to have a Center for Exposomics and Metabolomics, for spatial statistical analysis, for exposomics and health disparities, and for innovation exposomics. We're going to develop some of the assays and devices that are going to be used in the future. And as part of our capital campaign, we're going to be hiring quite a few faculty in the next 5 years, some of whom hopefully will present at this symposium going forward. But we want to link exposomics to all diseases. We want to link it to every department and every institute across Mount Sinai, because just as every disease has a genetic component, every disease has an environmental component, and we're going to build that environmental component. Thank you. So I think we'll go straight to Dr. Niedzwiecki, and we'll hold questions for the panel discussion at the end.
Hi. So today I'll be talking about how here at Mount Sinai and actually elsewhere, we're using cutting-edge metabolomics technologies to understand the exposome. So as was mentioned earlier, the exposome refers to the totality of environmental exposures and the biological responses to these exposures throughout your entire life, so from conception until death. Here's a schematic that explains how we're thinking of when we're thinking of the exposome. On the left is what's known as the external exposome. So this refers to all of the exposures that can occur in your environment. These might be specific things like from your diet or smoking, or more external things like climate change. In the middle is what's known as the internal exposome. This refers to all of the external exposures that actually make it into your body, in addition to the biological responses to these exposures. So in this paradigm, your health risks and your disease risks are the results of your external exposomes and your internal exposomes and the interactions among them. So I don't think anybody who's a proponent of the exposome concept truly thinks it's possible to measure the totality of exposures. But I think the importance of this paradigm is that we're trying to emphasize a more comprehensive approach to exposure assessment. So this means moving beyond just looking at a single exposure and looking at how they occur in mixtures. Trying to understand the biological responses to these exposures so we can get a better idea of the inter-individual variability in responses. Also understanding interactions, so how these environmental exposures interact with both external and endogenous factors. And really importantly for here at Mount Sinai, we're really interested in understanding exposure timing. So understanding whether there are critical areas of susceptibility throughout the life course. So the technology that we're very interested in understanding, primarily the internal exposome, is metabolomics. Metabolomics refers to, quote, the study of the unique chemical fingerprints that biological processes leave behind. So thus the metabolome refers to the complete set of metabolites that are found in a sample. So this can be metabolic intermediates, these might be signaling molecules or hormones, or even environmental chemicals. So as you can see, this is supposed to capture truly the exposome. We think metabolomics is useful for exposomics and really broadly in scientific research for several reasons. Number one, it's high throughput, it's inexpensive. You can use it in blood, but you can also use it in a variety of sample types. Very importantly, you can identify metabolites that are linked to health outcomes that you weren't even aware that you were interested in. So it's really a discovery-based approach. And number three, importantly for environmental health, is we can really use this to link metabolomics to environmental exposures to get a better idea of these biological responses. So there are two approaches to metabolomics. There's targeted and untargeted. So for the targeted approach, this is really a good way to go about looking at a particular pathway. So say you're interested in, for example, the Krebs cycle. You would generally use targeted metabolomics to look at the metabolomic profile of that pathway. Here at Mount Sinai, we're interested in what's called untargeted. This is really global metabolomic profiling. So what this will get at is these unknown unknowns. So these are these metabolites that we didn't even know that we were interested in looking at. For untargeted, there are two different platforms that can be used. There's what's known as NMR, or mass spectrometry, or MS. NMR is really great if you're interested in a handful of really high abundance metabolites. But what we're interested in is really a broad coverage assay that can detect really low abundance things. So that's why we go with the mass spec approach. Here at Mount Sinai, we use what's called liquid chromatography, or LC-MS-based metabolomics. You can see on this graph here, LC-MS, compared to all the other metabolomics platforms, offers the highest sensitivity. So it's able to detect metabolites at a sub-nanomolar range. And it also has incredibly broad coverage. So you're able to detect thousands of metabolites within a single run. So this is a very simplistic overview of how this works. Essentially, you have a sample, you do some preparation, you inject it into the machine, and you need to separate out your metabolites according to their chemical properties. So with the platform that we have in the lab, we separate them out according to their polarity. After they're separated out, we use something called electrospray ionization, and it charges all of the metabolites. Because in order for the metabolites to be detected, they have to have either a positive or a negative charge. And then these adducts are sent to the mass spectrometer, and they're detected according to their mass to charge, or their M over Z. So what we get is a bunch of peaks. We get thousands of peaks. All of these peaks are defined by three characteristics. They all have a unique combination of M over Z, retention time, which is how long they stayed in the column, and the intensity, which is how much of that metabolite was present in a sample. So each metabolite that we're detecting within our sample has a unique peak or set of peaks. So for example, this compound, glycerophosphocholene, it's actually represented in our data set by 5 independent peaks. So when we get all of these peaks in the assay, what we're collecting is thousands of peaks, which actually represent all of the possible peaks from all of the possible metabolites that are in our sample. So it's a little complicated to identify what all of these peaks are. So what we do is a combination of a variety of approaches. In general, we'd use what's on the list as number 2 and number 3. What we do is we match the M/Z and retention times of the peaks in our sample to metabolites that we have in our in-house libraries and also against databases that are available online. And then what we can do is if we want to validate the identities of any of these compounds, we'll go back into the lab and we'll do some extra validation. So we're interested in metabolomics for a variety of applications, but one is looking at how we can use metabolomics to better understand the etiology of different health outcomes. So this is a really cool example from one of the metabolomics experts in our lab, Lauren Petrick. This is a study that she's working on in collaboration with some of her collaborators at, I think, Berkeley University. So this is a study of dried blood spots that were collected at Perth. And they conducted a case control study where they had cases of acute lymphoblastic leukemia and then healthy controls. And what they did is they used untargeted metabolomics in the blood spots to see if there were any metabolites that were present at birth. So this was prior to the onset of the disease, to see if there was anything that they could identify that was predictive of leukemia. So in this image, what you can see, it's just a visualization of all of the metabolites that they were able to detect in the blood spots. They're colored according to their biological functions, and they're grouped according to their correlations with one another. What they found was that among the thousands of metabolites that they detected, there were 24 that were able to discriminate the cases and the controls. And when they built a model, they were able to find that these 24 metabolites predicted whether the children were going to develop leukemia with 83% accuracy. So this is really cool. I mean, it obviously needs to be validated, but it shows the promise of these assays to identify things that could predict the onset of future health outcomes. We're also interested in trying to link metabolomics with environmental exposures. This is another really cool study that was conducted by one of my collaborators at Emory, where they used untargeted metabolomics to understand what's happening when people are exposed to a compound called trichloroethylene. So what they did was they looked to see among all of the thousands of metabolites that were detected, which of them were really strongly associated with trichloroethylene exposure. So on the left is what's called a Manhattan plot. And this shows all of the features that they found that were very strongly associated with exposure to the chemical. And in red are the chemicals that they detected that contain chlorine. So what this means is that these are probably metabolites of trichloroethylene that people didn't even aware were in the sample. On the right are the biological pathways that were shown to be perturbed, that were shown to be perturbed by trichloroethylene exposure. And then what they did is they actually integrated some of the metabolites that they detected in the untargeted assay with some immune response biomarkers and other health outcome biomarkers. And what they found was that the metabolites that they detected in the untargeted assay were both associated with the validated biomarkers as well as some of the biomarkers of immune response. So what they were able to do was try to really understand what's actually happening when people are exposed to this exposure. And then finally, we're trying to integrate metabolomics with technologies that we can use to better understand what's happening when we're exposed to things in the environment. We're interested in looking at the exposome in human cohorts, but what this is going to require is that we have these non-invasive monitoring tools in order to do more frequent assessment of exposures. So looking at exposures over time. One that I think many people in the room might be familiar with is what's known as the exposome band. What you do is you wear it, and the band actually absorbs many of the chemicals that you're exposed to in the air, and then you have it on for a while, and then you send it back to the lab, and they will analyze all of the chemicals that are in the band. So this is great for the external exposome, but we're interested in trying to find something for the internal exposome. So if there's a way that we can do a relatively non-invasive monitoring of a biofluid. So what I'm working on with some collaborators at Emory and at Georgia Tech is what's known as a microneedle patch. So this was originally developed as a way to deliver vaccines. So basically what it is there's a patch, and it contains an array of microneedles that are attached to the patch. So it was originally developed where the vaccine would be in the patch, and you would put the patch on, and the vaccine would be delivered into your epidermis. So we had the idea that we could actually reverse the flow. So what we would do is we would have the patch, you could put it on, it would actually sample your ISF from your skin, and then it would be collected in the patch. So the idea is that we can have this patch that we can use in cohorts. So we can send somebody a patch, they can put it on for a day, it can collect their ISF, and then they can send it back and they can analyze what's actually present in the ISF in the lab. So our first step was just to see what can we detect in ISF. So this is a study that I just published where we looked at the metabolomic profile of ISF. So using untargeted metabolomics, we just wanted to see what could we actually find in ISF. And with high confidence, we detected hundreds of metabolites of both endogenous and environmental origin, such as pesticides, for example. And then we were also able to see whether we could identify metabolites in ISF that were either elevated in ISF or very strongly correlated between ISF and plasma. So what we did was we were able to characterize these metabolites and then find out what are their biological functions. So I think what this shows is that ISF really can be used as a way to monitor the exposome, and we're really hoping that these microneedle patches will be helpful in cohort studies of environmental exposures moving forward. So I think finally, I think the number one thing that we need to consider moving forward with these studies is that we need to do a better job of integrating metabolomics with other approaches. So number one is figuring out how do we move forward with metabolomics where a lot of these assays are highly variable. So from lab to lab, the numbers can change quite a bit, sort of depending upon the preparation and the approaches that they use. So doing a better job of trying to standardize the approaches and protocols between labs, and then also figuring out approaches for how we can integrate metabolomics with other omics technologies. Number two, I think what's really important for the studies that we're doing here is trying to understand how to better integrate the external and the internal exposomes. So I think we'll be talking about some more of these external exposures later on in the morning, but figuring out, can we integrate air pollution or these social stress factors with metabolomics to better understand what's actually happening. Number three, cohorts, figuring out how we can better collaborate with other cohorts and build consortiums so we can actually have the numbers to test some of these questions that we have in relation to environmental exposures. And then I think finally, I think people act like metabolomics is going to be the answer to all of our problems. But I think what we need to do is do a better job of trying to balance these more discovery-based approaches with experimental. So when we find something in metabolomics, we need to actually go back and design experiments and make sure that these things that we're finding are real. But I think what this shows is that this is going to require efforts from everyone. So it's a really exciting thing. So anyway, thank you very much.
Thanks, Megan. So my name is Alan Just, And Megan just gave us a really wonderful overview of some of the analytic chemistry and approaches for measuring biological specimens. I'm going to talk about another aspect of this exposomic concept, thinking about the external exposome. And I'm going to talk specifically about how we can apply principles of remote sensing to measure environmental exposures, in this case from 700 kilometers up. So the field of exposure science, we're dipping into that this morning. I'm going to talk about some applications of remote sensing and geographic information systems, which can complement, as Megan said, some of the tools that we can use on biospecimens or data that we can collect directly from participants. Some of the advantages of these approaches is that you can generate place-based exposures. So if you know where someone spends most of their time, you know where they live or where they work, you can reconstruct something about their environment. That makes this method pretty scalable. We can apply this to large populations. We can use registries, large data sets. The burden on participants in research studies is quite low because you have to obtain a residential address history, for example. And we can sometimes capture and characterize complex or social factors which are not easily measured otherwise. So I'm going to give a couple examples, and I'm going to start with temperature and PM 2.5, fine particulate air pollution, very fine particles that can get into the lower airways, and we know are associated with lots of adverse health effects, including respiratory and cardiovascular health effects. So satellites have sensors on them, kind of like the analytic chemistry that was explained in the metabolomics. Those sensors, they're going to measure wavelengths of the electromagnetic spectrum, and by measuring that light that's coming off of the Earth's surface, they can be used to reconstruct many different kinds of parameters that we're interested in. So we can get measurements of land surface temperature from thermal infrared sensors. And for our air pollution models, we use something called aerosol optical depth. So it's how much light scattering there was that's attributable to particles in the whole atmospheric column. And it's a useful parameter because it's related to air pollution, but I do most of my breathing wherever I am in the bottom 2 meters, and so this measurement that's going all the way up in the atmospheric column, we need to do some work with that. The product that comes from NASA is not a direct measurement of air pollution. And so this is, we can integrate this data, and in the case of air pollution, I'm going to give an example here of how we built an air pollution model for Mexico City. So Mexico City is a large metropolitan area, in one of the largest in the world, largest in North America, and it has some ground monitors that are measuring air pollution throughout the city, but not very many. And so if you were trying to do a health-based study and you had just those ground monitors, maybe you'd have to attribute people to the air pollution of the closest monitor. Maybe they don't live very close to a monitor. There's been a lot of work in the air pollution modeling community to layer on other kinds of information, the technique called land use regression. So maybe you can account for whether or not people live close to roadways, what's going on with meteorology or land use. Often this has been used when you're looking at a long-term average of air pollution exposure, but it's harder to get at the day-to-day variation that's happening where people live. But what we're adding to that is this satellite remote sensing measurement that we're getting from NASA's satellites. And so by bringing all of this information together, sort of a hybrid approach, we can reconstruct exposure measures that vary in space and time. And then we can look at where someone lives and can reconstruct an exposure profile for that person that goes back in time And when we're interested, as other speakers have mentioned, in critical windows and susceptibility that's related to the timing of biologic processes, we can reconstruct exposures during that time period. So we did this in Mexico City, as I mentioned, and the sort of product here is a 1 by 1 kilometer grid. So that's a pretty fine area that has daily estimates of air pollution going back to 2003. So for example, we work with a cohort where we recruited women who were in mid-pregnancy between 2007 and 2011, and we can go back and we can see what was the air pollution at the address where they lived, during that period of early life. I mentioned that we can use thermal infrared to get land surface temperature. We can also use our modeling techniques to reconstruct what the ambient temperature was, right, the air temperature. And this is also using NASA's MODIS instruments. So NASA has 2 satellites that we're primarily using. NASA's many satellites, but we use the spectrometer instruments on the Aqua and Terra satellites. They went up in 2000 and 2002, so we can go back quite a few years at this point. And we can reconstruct daily, again, 1 kilometer resolution temperatures, which allows us to look at things like intra-urban variation in air temperature. And we can assign temperatures based on where you live or where you work to try and understand and reconstruct the role of temperature in health, right? We know that extreme temperatures can contribute to heat exhaustion or additional physiologic stress. We can bring that data into the sort of emerging paradigm of how extreme temperatures that are more common under the emerging climate change scenarios, how those are contributing to adverse health effects. So our detailed reconstruction of temperature in space and time, along with air pollution and other kinds of factors that we can measure, is going to enable epidemiologic work that has been difficult to do, because historically a lot of work on temperature has been based on monitors at airports or particular meteorologic stations, and haven't necessarily been able to account for rural or suburban populations as effectively. Our colleagues have demonstrated that these methods, when you can reconstruct the temperature where people live, that they see on the high end, higher temperatures are associated with slightly lower birth weights, and that you can't see that association as clearly if all you have are the fixed meteorologic stations, right? If you said, you're either going to get assigned the temperature from Central Park or the temperature from LaGuardia. So the strengths of these sorts of approaches, where we're using satellites, sensors, and we're merging in other kinds of information to do this statistical reconstruction, is that our results give us a daily prediction. And with that temporality in the prediction, we can use epidemiologic approaches to look for those windows of susceptibility and understand whether there's a specific time period that's associated with the health outcomes that we're interested in, whether those be birth outcomes, as I mentioned, or respiratory health events, asthma attacks, et cetera. And so that allows us to both look at something that's short term. So was it something about the air pollution yesterday that might have been contributing to the health effect that you have today, or long term, right? We can aggregate it up. Was it something about the exposure throughout pregnancy or throughout the year prior to your stroke? And so this is a prospective measure, because these satellites have been collecting data continuously. So I mentioned 2 satellites, Terra and Aqua. Both of them go overhead every day, and once during the day and once at night. And so there's just an enormous quantity of data available that we're trying to apply here. So right now we're updating a model to give you a sense of the scale over the New England Mid-Atlantic region. So it's 13 states. So for every single day, we're reconstructing 600,000 predictions, and we're doing this now for 16 years. So we're generating about 3 billion predictions that we can then plug in to any health-based study in these areas, whether that's a state registry or an individual cohort that has collected address information from its participants. And we're using some machine learning algorithms. We're taking computational approaches that are more scalable so that we can address even larger areas with these 1 kilometer resolution models. So while we're sort of starting with New England and the Mid-Atlantic, we're also now working on continental scale models. And I'm going to just mention 2 examples of the kind of epidemiologic studies that we use with these resulting predictions. So one that we have going on, a collaboration with colleagues at Columbia, is to look at hospitalizations in New York State related to cardiovascular events, starting with strokes and myocardial infarctions, and looking at how extreme temperature and temperature variation in the temperature variation, meaning the change in temperature, how do those relate to the events that people have had, this acute relationship, and you can look at the time period directly prior to someone having an event, and you can compare that. Your control can be other time periods in the same month, matched to the same day of the week. And you can tease out that short-term association. And then an example of searching for windows of susceptibility is some work that we're doing with a technique called distributed lag modeling, where we're looking at these air pollution and temperature dynamics throughout the pregnancy period and linking that to birth registries. So hundreds of thousands, and eventually we'll get to millions of birth records to understand. I mentioned that higher temperatures are associated with lower birth weights, but we're going to try to tease apart, when is that occurring? Is that specifically related to the later pregnancy period where you have sort of the most the fetal growth going on? What's going on? Can we understand the susceptibility? Because then we can target prevention, right? We can figure out the specificity of timing in these associations. There's other things that we can measure. Dr. Wright mentioned light at night, in particular for some of the air pollutants. I've talked about fine particulate matter, but also these sorts of approaches can be used with ozone, with NO2. I've talked about surface temperature. We can measure greenness, so we can capture the intensity of vegetation. Commonly used is the normalized difference of vegetation index, and here this is a false color representation of the New York area. So it's sort of scaled red to green. That's not the true color, but it's an index that's showing us the density of vegetation, and we can do this on very fine scales. So we can look at a 30-meter resolution. And new sensors are creating some new opportunities in this field. So I've mentioned these 2 satellites that went up in 2000 and 2002. They're essentially the sensor technology of the 1990s, and it's amazing that they're still working because they were originally supposed to be operational for 5 years each, and no technician has worked on them since then. But the new sensors, they've had this incredible advancement in technology, and so I'm very excited about one particular satellite that's now known as GOES-16. It was called GOES-R when it was launched. It's operated now by the NOAA, and so GOES-16 is pretty cool because it's in geostationary orbit, which means that it's parked over North America. And so instead of 1 overpass a day per satellite, it can do images every 5 minutes. And so the volume of data that we're going to be able to access and the ability to reconstruct what's happening even within the day is going to be incredible, right? And you're going to start to look at dynamics where you have a buildup of pollutants, during the day, there's sort of early traffic, the mixing height layer, the atmosphere is low, and then, maybe at night it's dissipating. We're going to be able to reconstruct what's going on with the temporality of the urban heat island effect, where we know that the paved surfaces and lack of greenness in the urban areas means that we hold on to our heat at night, and we're going to be able to really tease that apart and understand what's happening. So I think that this is a very exciting time to pair these kinds of approaches and technologies using remote sensing. I spoke a little bit less about geographic information systems, but that's a software tool that's used to bring together this consideration of how things relate in space. And so, I mentioned that we can measure greenness or vegetation. This is an example from Mexico City, where we're using that 30-meter resolution. This is from the 30-meter we use from the Landsat series of satellites that go back, even further. These satellites, they're not just covering the US, they cover the globe. I mentioned that we do a lot of work in Mexico. I'm going to Basel, Switzerland on Saturday to work with some colleagues on some models in Europe, and we've done some of this temperature modeling in Israel as well, where you have very hot climate in southern Israel, and a lot of variation because they also have the Mediterranean coast there. So we're going to be undertaking now, I mentioned the scalability of these models and the size of these models, right? So we started with New England and the Mid-Atlantic, those 13 states. That's 1/11 of the continental United States. So we've got a really large volume of data, which is an exciting challenge for people who are more computational. And this is going, once we've reconstructed temperature and fine particulate matter across the United States, that's going to allow us to examine which kinds of populations are more susceptible, to look at disparities, to understand the differences between urban, suburban, and rural populations. And I think that it's really a breakthrough moment in using remote sensing tools in application for public health. Questions at the end, but I'll turn it over.
Thank you very much for that. It's always nice for us as well to step back and look at all the things that are developing in the field. It's very exciting to just sit back and hear these talks for ourselves. So hopefully you're feeling the same way. I just want to remind people before we go to break, you have index cards in the folders that you obtained when you came in. And if you want to write your questions for the Q&A session on those cards, you can give them to Megan Markham. Megan, can you raise your hand? I'm going to have them pass the cards to you. If you have some during the break already, we can start compiling those, but please start filling out the questions. You can step up and ask the questions too, but this way we can actually get going right when we have the session starting. So we're going to take a break now until 10:55, is it? 10:55, we're coming back, and we'll do the last two talks, and then we'll have a good long Q&A session. So please look for the cards and start putting your questions on there.